right, good morning, everybody. I have not even had a chance to look at the exams yet. I'll definitely have them done by the end of the week, maybe earlier. But I have not even had a chance. I was gone all weekend. But anyway, today I'm going to start 4.6. Which is entitled Optimization Problems. So, again, the idea with calculus is we learn things that we need to know to be able to take derivatives. We learn limits, review functions, all that stuff. Then we learn derivatives, and then we learn to take derivatives of all types of functions. And then in chapter 4, we're using derivatives as applied to different situations. And in this section, it's the same case. We're going to use derivatives to solve problems, to find the optimal solution to a particular problem that they're describing. The calculus is really the same thing that we talked about a few sections ago with finding minimums and maximums. That's all it is. It kind of makes sense if you're trying to find the optimal solution. Usually that is a minimum or a maximum. So there's not really any new calculus stuff. We're just finding minimums and maximums. Of course, we already did that, but we did that before with just functions in general. We just had a function and they said maybe find the absolute minimum or maximum, maybe relative minimum or maximum. In this section, what's different is the problems are in the form of word problems. Somehow these word problems are going to lead to a function that we can create, and then we're going to find most likely the maximum, sometimes a minimum, but most likely a maximum solution to this problem they're describing. So they'll say something like find the maximum area or the shortest distance or something to that effect, and they'll describe some situation. So the idea is take the problem that they're describing, write a formula for the function, and then find the maximum or minimum. I'm going to start with a relatively simple one, number 1. I'm going to jump right in here. It says find two numbers whose difference is 196. And whose product is minimum. So the idea is we got to find these two numbers. They give us this restriction or relationship between these two numbers. If you were to subtract them, the difference is 196. So maybe 204, the difference there would be 196. But we want to find the particular pair that if you were to multiply them, the answer you get from multiplying them is as small as possible. So this right here is just a relationship between the numbers, a constraint. This is what we're trying to optimize, find the minimum. If I try to take what they're saying there and write it down in terms of mathematical equations, they're saying two numbers whose difference is 196. So there's two numbers we don't know, x and y. But if I subtract them, it's 196. So that's what they're saying right here. Whose difference is 196. But the function that we're trying to optimize is the product. So I'll use product, P for product, means multiply. So we're trying to minimize this function. The idea is P for product. It is a function of x and y. It depends on x and y. So it is a function, it's variable, it's a variable. It can change for the different values of x and y. Of course, the problem is with this formula for function, we got an x and a y in there. We'd like just x's. So this constraint up here, we could solve it for one of the variables and plug in down here so that we only have one variable. If I simply add y to both sides here, I can isolate the x. And the x is 196 plus y. So if I take that expression and plug it in here for the product, x is the same as 196 plus y. Then the product has this new formula, 196 plus y times y. So now there's only y's. Now it looks more like a traditional function, traditional formula. In fact, I can use the function notation now. The product, which now only has y's in it, so the product as a function of y is 196 plus y times y. So there's the formula that I need to try to optimize. In particular, trying to find the minimum. So that means find the derivative, find the critical numbers, find which one is a minimum. Over here. The product formula, it's a function of y, is 196 plus y times y. If I distribute the y, then it looks a little better, I think. 196y plus y squared. So I want to find the minimum. So I need to take the derivative. Derivative of 196y is 196 plus power rule there, 2y to the 1. Find the critical numbers there. Critical numbers happen when the derivative is undefined or 0. It's never undefined here, but it is 0 at whenever y solves this equation. Just set it equals 0. Solve for y. 2y equals negative 196. Divide by 2. Y equals negative 98. So we know the critical number, negative 98, could possibly be a minimum or maximum. Don't really know. Most likely it's a minimum, but I'm going to check and see. So on my number line, I only got this one critical number, negative 98. So we get negative infinity to negative 98. The derivative is either positive or negative. Can't change though. Negative 98 to infinity. Same thing. It's either positive or negative. I don't know which way. So pick a test point. First, for this interval, pick some number that's in that interval, plug it into the derivative, see what happens. See if it's positive or negative. So like negative 100 maybe. There's a formula for the derivative. If I plug in negative 100, I get negative 4. But what's real important is it's negative. So that means the function is decreasing up to the negative 98. Most likely this interval it's increasing, but we need to check to make sure. So pick a number, plug it in that's in that interval. Pick whatever you want. I'll do 0 just because it's easy to do calculations with zeros, and 0 is in that interval. Yeah, 196, but again, positive. So negative to positive, which means decreasing, the function is decreasing then increasing. So it's doing something like this. So that confirms that it is definitely a minimum at negative 98. So we got minimum at y is negative 98. That's not the complete answer though, because I say find the two numbers. We got one of them, negative 98. We need to find the other one. But we've got this formula that relates the two. Here it was to begin with. But it might actually be easier to deal with this one, since it's solved for the x. I know y now, but for the x. Y is 98. X is 96 plus y. 96 plus negative 98, which makes positive 98. So the two numbers are 98 and negative 98. That's the answer to the question. This is one of those problems, though, where you do have to put the numbers in the correct box, because they want the smaller one in one box and the bigger one in the other box. So, of course, this is the smaller one, so this one would have to go in the box that's labeled smaller number. This one labeled larger. Yes.
Never mind.
Okay. I also want to point out that this is an exact problem you may have seen in like a college algebra class. But there you do it differently. There, this leads to a quadratic equation. This formula here that I set up is quadratic. It's got y squared, which implies it's a parabola. And so the vertex of the parabola is the minimum. So that's how it was done in college algebra. Now we're doing it differently. Same problem, but now with calculus, with the derivatives. Verifying that that is the minimum. You might actually say it's a little longer doing it this way, finding the derivative. Probably is. But we can do a lot of different types of problems that you can't be doing in college algebra, because in college algebra you can only do the quadratics. And we're going to see a lot of functions that are definitely not quadratic. Just this first one was. All right, so that one is number one. Generally, they start off easy and get harder as you go. Generally, it's kind of the case here. This one wasn't really in the form of a word problem, other than it was written out in words, but it wasn't describing some real world situation like planes flying or people walking or something of that nature. Here's one that's a little bit harder. Number 4. It says a rectangular storage container with an open top is to have a volume of 10 cubic meters. A rectangular storage container with an open top. Is to have a volume of 10 cubic meters. Of course, there's a lot more there, but I want to point out something. Rectangular storage container. So like a shoebox. That'd be a rectangular storage container. And it says with an open top. So it's like a shoebox with no top on it. It's got the sides and the bottom with no top. Of course, this is a lot bigger than a shoebox. Just 10 cubic meters is huge. And whenever I hear this number or something along this, I think about concrete trucks and those big concrete trucks that bring concrete to work sites and so on. They measure the concrete in cubic yards. And generally those trucks have 8 to 10 cubic yards. And a yard and a meter is close to the same. So this is about a whole semi-truck worth of cement in this container. And by the way, also, when they talk about cement trucks and how much the trucks will carry, they won't say cubic yards. They'll just say it carries 9 yards. But of course, the implication is it has to be cubic yards. It has to be a volume, not a length. But anyway, we're dealing with something that looks like a great big shoebox. There's lots of ways we can construct this shoebox. It could be maybe real deep, narrow, but has a volume of 10 cubic meters. Or maybe it's not so tall, but it's really wide and really long. It doesn't matter the shape as long as it has 10 cubic meters. The goal is we're going to figure out the shape. Anyway, reading on, it says the length of this base is twice the width. Length of this base is twice its width. So they're giving us a constraint here. They're saying the length of the base has to be twice the width. Then there's still a lot more there, but I'm going to go ahead and draw a picture right now. They're saying that we got the shape. It kind of looks like a shoebox. It's a rectangular storage container. It's supposed to be a three-dimensional shape that looks like a shoebox. They're saying the length. Now, if I call this the length, they're saying that length has to be twice the width. Of course, there's another dimension they haven't even really made reference to yet, the height. But what they're saying right here is the length has to be twice the width. So they're giving me the relationship, the constraint between these two dimensions. For example, if the width is 5 meters, if it's 2, this has to be 4. If that's 3, it has to be 6, so on and so forth. So they're explaining the length in terms of the width, so I'm going to call the width x. Then I can make an easy expression for the length. It has to be 2x. And I don't know exactly what it is, but I can create this algebraic expression for it. X and 2x. Anyway, reading on. Now they're talking about the material used to make this. They say the material for the base costs $10 per square meter. So the base is the bottom. The bottom costs $10 per square meter. The bottom down here. Material for the sides costs less. It costs 6. Per square meter. So the bottom costs more than the sides. Maybe because it has to be thicker or something because it's supporting more weight. I don't know, but they're saying the bottom costs more than the sides. And again, the idea is this can be about any shape. I mean, you could have one that's got a real big base, but it's not very tall. As long as the volume is 10 cubic meters, you'll satisfy that. Maybe instead it's got a smaller base, but it's real tall. It still has a volume of 10 cubic meters. And of course, the goal is to figure out the dimensions that will make the cost as small as possible. Find the cost of materials for the cheapest such container. So cheapest, of course, minimum cost. So that's why there's problems in this section as well. We're trying to optimize this problem. It's a minimum again, find the cheapest container. The ultimate goal is to find the cheapest cost. But of course, what we're going to have to do is find the dimensions first, and then from that calculate the cost. So we need, of course, a formula for the cost. And the cost depends, of course, on the shape, and then how much material is used on the bottom versus the sides. So here we go. Cost equals, I'll do the bottom first. It's the most expensive part in terms of cost per square meter. It is $10. So I'm going to take 10 times the area of the bottom. The bottom is just a rectangle, so it's length times width, so it's x times 2x. So that's for the bottom. Then I need to add in the sides. There's 4 sides altogether. But the front and back are the same, and the left and right sides are the same. So even though there's 4 sides, really I just need expressions for front and back, multiply by 2, left and right, multiply by 2. So for the front and back, since it's front and back, I'm going to multiply by 2. And it only costs $6 per square meter. And then I need to multiply that times the area of the front and back. So for the front and back, we got this width x, and then we got this other dimension, the height. That is not expressed in terms of x. So I need a variable for it, so I'll call it h for right now. So for the front and back, it's x times h. It's the area of the front. Likewise, it's also the area of the back. H times x. So that's front and back. And just make sure it's real clear. Multiply by 2 because it's the front and back. There's 2 of them. $6 per square meter. And then the area is h times x. Now for the left and right. Same thing, there's going to be a factor of 2 because there's a left and right. They're the same. The left and right also cost $6 per square meter. And then the area of the left and right is, so it's a rectangle again, so it's length times width, but in this case, I'd call it length times height. So it's 2x times h. Two x times h. So, I should put here too. This is left and right. So if I simplify things a little bit, that could be rewritten as 20x squared plus 12 hx plus 24 hx. I can combine these to make 36 hx. So there's a formula for the cost. But again, I've got two variables in there. I've got the x's and I got the h. I need to fix them. Only want one variable. I haven't used the fact that the volume has to be 10 yet. That's the constraint. That's what's going to relate the x's to the h's so that I can substitute in to that equation for the h and only have x's. So I'll set that aside for a second. They say the volume has to be 10 cubic meters. The volume is length times width times height. Writing it out in words. And they say the volume has to be 10 cubic meters. Give me a fixed number. The length, 2x. The width, x. And the height, h. X times x makes x squared. If I divide by 2x squared to isolate the x, because the idea is I want to put it in over there and I only have x's. If I divide by 2x squared, and I can simplify this to 5 over x squared. Not that it really matters, but if I reverse it around, h is 5 over x squared. So now I can take that, plug it in for the h over here, and get a formula for the cost that only has x's. Now it only has x's, so my cost function now only has x's. So I could use the function notation now. The cost as a function of x is 20 x squared plus 36 times 5 is 180. And then this x cancels with one of them here. So I'm left with an x in the denominator. I'm going to rewrite that as x to the negative 1 just to make it easier to take the derivative, because that's what happens. So anyway, there's my cost function now as a function of x only. Only has x's in there. So it took a whole lot of work just to get to the formula. Again, when we did maximums and minimums before, they gave us the formula. And the maximum and minimum of this. These word problems, we have to take what they're saying and construct it. So it takes a lot of work just to get to that. But now we need to find the minimum. We want to find the cheapest or the smallest or the minimum cost. Notice this is not quadratic, so we couldn't have done this in college algebra. It does have an x squared there, but an x to the negative 1 messes that up. So we do have to use calculus here, take the derivative, find the critical numbers, test them, and see which one's better. So the derivative, let's use the power rule. This time, 2 drops down, subtract 1. Same thing here, power rule, negative 1 drops down, subtract 1. So the derivative is going to 40x minus 180 x to the negative 2. Negative 2 is same as denominator x to the positive 2. I can rewrite this as 40x minus 180 over x squared. I used the negative exponent just to make it easier to do the derivative, but after I did it, then I could write it back like this. So anyway, there's the formula for the derivative. You need to find the critical numbers. Critical numbers are where the derivative is 0 or undefined. Now, this would be undefined at 0. Because I'd have 180 over 0 squared, 180 over 0 undefined. But because this is coming from some problem that they're describing here, could x really even be 0? No. So I don't need to actually worry about it, because if x were 0, that would imply that the width is 0, and then the length, it's double that. The double 0 is still 0. So it'd have no width, no length. The height would be infinity. So it just wouldn't make physical sense. You can't have a shoebox with no length, no width, and infinite height. So we only need to worry about, though, where the derivative is 0. So take the derivative, set it equal to 0, and solve for x. So I need to solve this equation first. Whenever you're solving equations and it's got a fraction in it, best thing to do, not the only thing, but the best thing in my opinion is multiply by the denominator. If you got more than one fraction, multiply by the least common denominator. Because that clears out the fractions. I'm going to multiply both sides by x squared. Of course, when I multiply on this side, it's still 0. On this side, I have to distribute. X squared times 3x minus x squared 180 over x squared. And then these cancel. Which is what I was after. X squared times 40x makes 40x cubed. Minus 180 is all that's left there. 0. Add 180. Divide by 40. X cubed is, see, that reduces. They both end at 0, so I know they're divisible by 10, so that'd be 18 over 4. But then that reduces further because 18 and 4, they're both even, so 9 over 2. To get rid of the third power, I take the third root. I don't get a plus or minus because that's odd. If it were even, like I had to do the square root or fourth root or sixth root, I'd have a plus or minus, but not for an odd root. Just get 1. Cube root of 9 over 2. So that's the only critical number. You could maybe almost assume that that's got to be a minimum, because it's the only critical number that we got. The goal is to find the minimum cost. But I do want to verify it. So I'm going to test my, let's see, my derivative right here. So I've got the interval 0 because the x can't be smaller than 0 up the cube root of 9 over 2, and I got that critical number, cube root of 9 over 2, then cube root of 9 over 2, and infinity. The idea is the derivative is always positive in here or always negative, but it can't change, and then likewise. Most likely it's going to be negative than positive. Give me a minimum, but I do need to check to make sure. Now, checking can be kind of tricky because cube root of 9 over 2 to me doesn't make a whole lot of intuitive sense of what that number is. But if you think about, I don't know, 8 over 2, that'd be a little smaller than this. But 8 over 2 would be exactly 4. Cube root of 4, what's that? Well, square root of 4 is 2. So cube root's going to be a little smaller than that. But of course, I could just type it in the calculator to get a rough idea of what that number is. I do type it in cube root, parentheses, 9 divided by 2. I get 1.65096. So close to 1.6. And again, the reason I did that is because I want to make sure that I am picking a proper number that is definitely in this interval to test it, to see if the derivative is positive or negative. So 1 would be in that interval, because 1 would be smaller. So let's see what the derivative at 1 is. If I plug in 1 into the formula for the derivative, I get 40 minus 180, negative 140. But again, all it really matters is whether it's positive or negative. And this is negative, which means decreasing. The derivative is negative, so that means the function is decreasing. Over here, most likely it's now increasing, but I'm going to test to make sure. This is about 1.6, then 2 would work as a test point. If I plug in 2 into the formula for the derivative, 80, 40 times 2 minus 180 over 2 squared. 80 minus 180 over 4. 80 minus 90, 45. I get 35. And what the actual number is not really important, but whether it's positive or negative is. 35 is positive. That's what's important here. Which implies the cost function's increasing. So if it's decreasing, then increasing, it's doing something like that, then at cube root of 9 over 2, it is definitely a minimum. X equals cube root of 9 over 2. That's not the answer to the question, though. I'm close now, but the question, ultimate goal, is to find the cost of the materials for the cheapest such container. So I found out what X has to be to make that happen. This is the cost formula right here. So I need to plug in the cube root of X of 9 over 2 into this cost formula. So next one over here. In the cost formula, after I worked with it, got it as a function of X only. I found out the minimum happens at cube root of 9 over 2. Now they do say the directions round to the nearest cent, so decimals are okay. Take this, calculate it in decimal form, and then round to the nearest cent, which means 2 decimal places. So I know cube root of 9 over 2, I did that a second ago, 1.6 1.65096. 1.65096. I'll type that all in. 20 times 1.65096 squared plus 180 divided by 65096. 163.540854. You're sent two decimal places. I got a 4. Next thing's a 0, so that leaves you a 4. $163.54. There's the answer to the question. That's what they want you to enter as your final answer. All of these problems have kind of a similar format. They're describing some situation that has a lot of variables in it, like this had length and width and height of this container. But they put restrictions, like the volume has to be 10. They also say in this one the base is twice the width, so they got those restrictions. So they've given us those restrictions so that we can narrow down the formula to just one variable. And we construct some formula and then try to find the minimum or maximum. So they all have this similar format. It's just whatever they're describing is going to vary from problem to problem. Of course, once you set up the formula, we just find the critical numbers, minimum and maximum. But the hard part, in my opinion, to these problems is setting up the function. Some of these I think are really neat. I thought this one was kind of neat. Number 5, I think, is really neat. Number 5 says, find the dimensions of the rectangle of largest area. So right there, they're telling me I'm going to have to set up a formula for the area. And I'm going to try to find the maximum area. So I'm going to have to find a formula for area, find the critical numbers, test, and find the maximum. Anyway, they then tell us the constraints about this rectangle. They say that has its base on the x-axis. So base is bottom. The bottom of the rectangle is on the x-axis. And the other two vertices above the x-axis and lying on the parabola, given by y equals 6 minus x squared. And the other two vertices above the x-axis and lying on the parabola. Given by y equals 6 minus x squared. So, goal is to find maximum area of this rectangle. So we need a formula for the area of this rectangle. They're saying this rectangle is drawn in the xy plane with the base on the x-axis, and then the upper two vertices hitting this parabola. So what does this parabola look like? You don't have to be perfect, but I need a rough idea of what it looks like. First of all, is it a parabola that's U-shaped or is it inverted? It's inverted because whenever it's negative in front of the squared term, it's inverted. So it's upside down. Where's the vertex going to be?
6.
At 6 on the y-axis, yeah, because vertex happens at its maximum point. If x is 0, we get 6. Otherwise, you're going to be subtracting something, so it's going to be smaller. 1, 2, 3, 4, 5, 6. Vertex is there. So it's going to be upside down, inverted, look like that. So they're saying the rectangle's in here. It has its base or bottom on the x-axis and the other two vertices up on that parabola. So the rectangle looks something like that. Of course, there's a lot of different rectangles that would satisfy that. I drew a rectangle that touched the parabola here and here. But you could have a different one that touches over here. So it'd not nearly be as tall, but it'd be a lot wider. But you could have another one that touches up here where it's not nearly as wide, but it's a lot taller. So there's a lot of them you could make. The goal is to find the one that has the largest area. One more thing that I'll have to pause. Where does this parabola hit the x-axis? On my picture, it's here and here, but what numerical values would that be? Does everybody see? When it hits the x-axis, the y value is 0. So when the y value is 0, what would the x be? Huh? 6, I hear it. Square root of 6, plus or minus. Because if the y is 0, 0 equals 6 minus x squared, so x squared is 6, take the square root. If there is a plus or minus, because it's an even root, plus or minus square root of 6. So right here, that's square root of 6. Down here, that's going to be negative square root of 6. That's going to be kind of important because it gives the limits on what x could be. Like the biggest the rectangle could be is clear out here. The smallest it could be is in here. But anyway, I'm out of time for today, so I'll pause here. Tomorrow I'll continue on with this and finish it up. We got a good start here. See you all tomorrow.